Hello. In this part, I am going to demonstrate you the framework that I have developed uh, for design and analysis of algorithms, especially sorting algorithms. Okay. Now, if you look at your syllabus for design analysis of algorithm lab, which is PCCCS 494, you will find that there are some sorting algorithms that we have to implement, right? Now, if you look at the all the labs that are given in the syllabus, you will find that in everywhere we have to implement the algorithms. That is kind of we have to implement or we are basically practicing the designing part, right? Now, I thought since the course is design and analysis of algorithms, why not I do something for analyzing those algorithms? Okay, so for doing that, I have developed a framework where basically we are going to analyze the performance of the sorting algorithms, okay, and also the search algorithms. So what we have in the framework and how you will have to do that in this video, I am going to discuss that. Okay, so let me first show you what we have for you. So for running this framework, as you know that your lab you have to do it using C language, right? And for doing that, you have to or you have to use some ID, right? And the recommended ID for from my side is DevC, and this framework is also developed in DevC. Okay, so let us see what we have in the framework for you. So if you I will share a zip file with you, and if you unzip that, you will find this kind of structure. Okay, now what you have to do, you can find this algorithms.dev file, okay, which is nothing but a devc project file. Okay, so if you hover over it, it will tell you that it is a dev c++ project file. So just double click on it. Okay, now if you double click on it, you will find that there are a project is open on devc, and there are some binary search.c, heapshot.c, insertion shorts.c, linear search.c, merge sort.c, and quickshot.c. Now in your syllabus you have to implement binary search and probably merge sort and quickshot. Okay, now rest of the search and sorting algorithms you can implement of your own. And once I show you how this framework work and what you can do with this for analyzing these algorithms, I believe you will have fun of it, and you will uh, you will have to have you will get some interest on this topic. Okay, how to analyze this, how those charts are looking with the data. So this is going to be a fun for you, I believe so. So just let me go through. Once you have this project, you open this. So what we have, let me go through the linear search part. So in linear search, what we have, I have described over here what you have to do. So in linear search, if the search is successful, the function should return the index of the largest element in the array. uh, Sorry, in index of the target element in the array, otherwise it should return -1. Okay, now here and in this box you have to write the code for the linear search only. Now you do not have to take input. Okay, you do not have to take input, you do not have to show the output. What you have to do, all those things has been taken care of by the framework. You have to just implement the linear search algorithm within this function. Okay, now for doing that, you can write any other function as per your requirement, but don't change this name of this function. Okay, like linear search. So again, so for binary search also, this binary search you have to implement. For binary search also, if the search is successful, the function should return the index of the target element in the array. Otherwise, it should return -1 or some negative value. Okay. So this is what you have to return. This is what my framework is expecting from you, from this binary search to return. Okay. So if you find this, then it will you have to return the index, otherwise you have to return some negative value. Okay, now all the input to this binary search is given over here. Okay, so a is the array, okay, and size is the size of the array, and target is the value we are going to find out in the array, whether it is existing or not. Okay, so for doing that, you have to implement the binary search code within this function. Okay, now if you want to write some more function which you are calling within this function, you can write it, but don't change the name of this function. Okay, so let us show. So this is what for searching. So let us show the something for sort, like for insertion sort. If you look at it, so you know that since sorting an array, or if you change anything in an array, and since we are doing it C, uh, it is done by using the pointer, right? So array is nothing but pointer of the array, and pointer you can use interchangeably, right? So so what you can do, so whatever you do within the array, it will be reflected from where it is called, right? So that's why there is nothing to return from you, nothing, the framework expect nothing to return from you, rather it expect to sort the given arrays. Okay, so for all the sorting algorithms, you can see that there are two input, one is the array and another is the size of the array. Okay, and what you have to do, we have to implement the insertion sort over here. Okay, for merge sort, you have to implement the merge sort over here. Okay, so for merge sort, actually I have so you have the recursive function, right? So for merge sort, I have given two things here. A is your array, P is the starting element, and R is your uh, end element. Okay, so so what you have to do, you have to consider this. This is the start index and this is the end index, and then do the merge sort over here. Okay. Okay, let me check for the quick shot. So for quick shot also the thing is same. Okay, P is the start index and R is the end index. Okay, so uh, in place of size, since the quick shot and merge sort are done using using your uh, using recursive calls. Okay, so that's why this thing has been done. Okay, I mean in place of size, it is given the starting index and the end index over here. Okay, and for if short, it is given as the array and the size of the element of size of the array. Okay, so this is what you have in this framework. Okay, so let me now show you that what you have to do, what you will do with this framework. Okay, so this is what you will get, and once you get it, you have to implement. You have to, for this algorithm, for binary search, for merge sort, and for quick sort, you have to do this over here. I mean, you have to write just the code for this search part or the short part, not input and output. Okay, so input and output again has been taken care of by the framework. So let me show you how to once you write a code for over here, how to do the things. Okay, so if I go go to the dev part where I have actually written all the codes. So let me open it. So in this project, the same project, but here I have implemented the algorithms. Okay, so the codes are written. So let me show you linear search, which is the simplest one. So see, everything is there in the last project that I have shown you, in the algorithms dot dev project that I have shown you. Everything is over here. Plus here the code is implemented, the algorithm is implemented. Okay, so in linear search, this is the implementation of the algorithm. So this is what you have to do. Okay, similarly in case of binary search, you have to implement the algorithm only. All the input and output has been taken care of. Okay, now if you run this, what will happen? So let us run this, compile and run. So if I run this, see, you will get a menu based output screen where you are basically asked that which algorithm you are basically currently implementing or currently want to test. So I am currently testing the linear search algorithm. So I will press 1 over here. So just give the number associated with that algorithm. Okay. So since I am doing linear search, I am giving 1 over here as a choice. Press 1 and press enter. Now it will ask you that whether you are doing it for manual testing or for automatic testing. Okay. So my suggestion to you is, once you have implemented an algorithm, just test it by yourself. Okay, just do the manual testing first and see couple of test cases that whether it is doing perfectly or not. If it is not doing perfectly, then again revisit your code and do the changes that are necessary. Okay, and again do manual testing until your manual testing is okay. Then you go to after your manual testing is okay, then you go to the automatic testing. Okay, so we'll have fun in the automatic testing. So what we have to do, so let us first show you what we have to do in the manual testing. So since I want to do the manual testing and which is number one, so I'll in my choice I'll press 1 and press enter. Now in linear search, what we have, I have an array of some elements, right? And I have to give a search target number which I want to search, right, in that array. So suppose I in that array I want 5 elements. Okay, and integer at index 0 is 1 and 2. Let me give it like that. So 1 to 5 is there, and next it is asking for the target value. So my target value, suppose is 6. Okay, so it will not it will do the linear search and it is not going to find out the element over here, right? So once I press 6 and press enter, it will show you the output that element not found, and the time is taken by this algorithm is 1100 nanosecond. Okay, so again if I run this algorithm again, if I run this algorithm and do a manual testing where the element is found. So if I run this algorithm and do a testing where the element is found, so again the same scenario, I am doing the manual testing for linear search, right? And I have given 1 2 3 4 5, and suppose I am trying to find out 1 in that array. So if I press enter, so it is telling that the element is found at index 0 and the search time is 700 nanosecond. Okay, obviously because in the last time the element was not in the array, so it should take higher time than this one, and it has done that, right? So this is what manual testing is. So once this is what you do when you implement an algorithm or when you write a code, right? So once you write a code, you test it like that. Okay, now let me show you what automatic testing is doing. So now if I run it again, so again I am doing it for linear search, and now I will press for automatic testing. Okay, now before I do it, in automatic testing there are some test cases given within the framework. In case of search algorithm, there are three kind of pattern. One is the search element existent in the middle of the given array. Next pattern is the search element does not exist within the array, and the third pattern is the search element exists randomly within the array. Okay, so this is what we have, three type of data, and for all those three type of data we have the input array of size 1000 to 15,000 with a gap of 1000. Means there are for middle element pattern we have 15 test cases of size 1000, 2000, 3000, 4000 up to 15,000. Similarly, for non-existent search element, we have data of 1000, 2000, 3000, 4000 up to 15,000. Similarly, for random existent data, we also have 1000, 2000, 3000, 4000 input array up to 15,000. Okay. So now let us see what will happen if we do the automatic testing with the linear search. So if I do automatic testing with linear search, so see it will run all the test cases automatically. Let me show you what the output is showing. So the first column is telling us the pattern. Okay, pattern middle element means for the given array and the search element exists in the middle of the array. Okay, and all this pattern you can see first 15 patterns are for middle element. Okay, now for this middle element pattern, the next column is size. So the size of the input array is 1000 in this test case. For size of the input array is 2000 in this test case, 3000, like that up to 15,000. Okay, next is whether your program is giving the correct result or not. So this is important column for you to check that whether you have done it correctly or not. So if this column is giving you no for any of the test cases, it means that your program might you have implemented your algorithm wrongly. So you have to correct that. Okay. So again, so this column is telling that for this pattern, for this size, your algorithm has given correct output. Okay. And finally we have the time in nanosecond. It means that for for this pattern, for this size, your algorithm is correct and it is taking it is giving correct output and it is taking 1200 nanosecond. So for all these 15,000 cases, we will have the time information in this column. Okay. You also have to check whether they are correct or not. Similarly, in the next pattern, we have non-existent. It means that the target value does not exist in the input array. Okay. So again, there are size variant of the test cases from 1000 to 15,000. Okay. And you have to also check that whether all of them are correct or not, and the time information is again given over here. Okay. Now again, the final pattern is you have random element, means the search element or the target value is existent randomly within the array. Okay, so again the size is from 1000 to 15,000, and for all the test cases the output was given as correct, and also the time information in nanosecond is given over here. Okay, next what you have to do. So now that we have three pattern of data, we have for all those three patterns we have test cases from 1000 to 15,000 with 1000 gap, right? And we have also found that our algorithm is giving correct output for all these things, for all these test case, and we also have the respective time information, right? How much time it has taken for the execution. Now what we'll do, we'll put this information in a spreadsheet and we'll make a chart out of it. We'll make a graph out of it to find out how the performance is. Okay. So what I have done, I have already done it for all the algorithms. Okay. So you can see I have done it for all the algorithms from linear search, binary search, insertion sort, merge sort, quick sort, and heap sort. So how we will put the data and how we will do that. So see, so first we have to put the data. Okay. So there are three things. The chart we are making is based on the size and the pattern, right? So see, we have the size in the first column, the the size of the input array. Okay, and in these three column we have basically the pattern of the input data. Okay, so middle element, non-existent, and random existent. And then what you have to do, then you have to put the data from this screen to there. Okay, so this data is a different one because I have filled this data from a previous execution of this algorithm. So this data for my case is not matching, but for your case, once you run this algorithm, once you get this screen, then you have to put the data over here. Okay, so you have to match it. So what you have to do, you have to take 1200 from here and put it over here. Okay, because this is for middle element 1000 size, right? So this is for middle element 1000 size. For middle element 2000 size, you have 2800. So you have to put it 2800 over here. Okay. And one more thing is, if you run this number of times, you will see that the time information is changing a bit because every time you execute it, the timing is going to change. Okay. The reason behind it is that this operating system is a complex one, and this model doesn't, this computer does not follow exactly the RAM model. Here we have the memory hierarchy things. Here we have multiple process running behind it. So the time information may change because of the context switching of the process and all. So you might expect some kind of graph, but you also can get what is not expected. Okay, I will also show you over here that some unexpected kind of information also unexpected kind of scenario can also happen. So so like that you have to put all the data. Okay, next you come to the pattern of non-existent. So non-existent 1000 is taking 2500 nanosecond time, so put 2500 over here. This is non-existent 1000 size. Next you have non-existent 2000 size, which is 4800. So we'll have to put 4800. So you can see that the data in the Excel which is from the previous run and data in the output screen which is from the current run is very near to each other, right? So in your case, if you run it several times, your data will be very near to each other. Okay. Now similarly, once you done for the non-existent, you also have the random element, right? So here again, random element 1000 size is taking 13,1300. Here 2400 again, the time may vary, and here it is taking very less time. Interestingly, because this is random element, so here the element is somewhere. Suppose in 1000 element, I have the data in 900th element, but here in the 2000 case, since it is random, it is probably in the 500th element. Okay, so that might happen in case of random. Okay, so again, all the data is put here. Okay, now once you put this data, next comes how you can get the chart out of it. Okay, now uh, from this data, if you want to make a chart out of it, so let me show you how you can do this. So first select the table. Okay, and this is for your Excel 365. Yeah, 365 or 2013, I cannot remember. Anyways, this is for Excel the 365, let us say, and if you have a previous version of it, you can also do that. Just if you don't know how to do it, just Google it, you can find how to make a chart of it. Okay, now once you select it, go to insert, and then you will find the chart options over here. Okay, so just click over here so that all the options come to you. So there are recommended charts, go to the all charts. Now for all this, what we are going to do, we are going to use the XY scatter chart. Okay, so remember, whichever Microsoft Office version you are using. Okay, if you do not have Microsoft Office, you have any other office, you can also do it over there. Just follow the respective steps for that. Okay, now but in whichever package you are doing, just do it with the XY scatter graph, and then this subgraph. Okay, which is basically scatter with smooth lines and markers. So where in this case the lines will be smooth and there will be markers of the data. Okay, so uh, whichever graph you are doing, just remember, do the XY scatter graph and then this scatter with the smooth lines and markers. Okay, now select any of this kind of no select this uh, type of chart and click OK. So see, the chart has now come over here. So what we have, see, we have the middle element as a blue and the marker is round. So as the middle element is blue, so this blue line gives you the timing information of the middle element, right? Now this is for the orange line is for the non-existent scenario, and the gray line is for the random existent scenario. Okay, so random existent may vary as well. So this is how you can uh, insert a chart for this data. Okay, and this is how now you can see that for linear search the charts are following basically linear kind of graph, right? The timing it is taking is kind of linear. Now you can see some glitches over here. For especially for middle and non-existent, you will find that this is almost linear, but will be some glitches, as I told you, because this is not perfectly a RAM model machine. This is there are several processes running behind by the operating system. So this timing information may vary. So all these things will be there. You can get some kind of charts which you cannot expect. Okay, so I am now deleting this chart because I have already made this chart. I have just shown you the steps how to make this chart out of it. Okay, so this is the chart. So for all of them I have the charts. Okay, now for binary search you have to do the binary search. Okay, you have to implement as per your syllabus. So you will find that probably in your case also you'll find this kind of graph is coming, which is not very consistent to our knowledge. And why this is coming? Because see, binary search is taking very less time, and for this 15,000 of data, I mean from 1,000 to 15,000 is nothing to it. Okay, so that's why this moreover, you know, the this is not a perfect DAM model and all, so that's why the timing, since the timing is very less, it is showing a bit unexpected curve. Okay, because you know that middle element uh, has to be always order of one, right? But you can see that the curve is getting ups and down, because for middle element it is sometime 200 nanoseconds, sometime 100 nanosecond, like that. So all these nanoseconds are very near, but again almost linear. I mean, if you see from yours, from our view, 200 nanosecond and 100 nanosecond, I mean we cannot even realize how much less time it is, right? Only 100 nanosecond. But since this is a graph of in nanosecond scale, you are feeling this curve over there. But once you get out of it in the second level, from nanosecond to second level, you will find that, or millisecond level, this curve is nothing but a straight line. I mean, almost a straight line. Okay, so if you look at this, there are some discrepancies in this curve as well. I mean, from the timing information, like whatever be the case. Okay, so the middle element in binary search has to be the last one, right? But you can see that, I mean, has to be the lower bound, or has to be the I mean, for these three cases, middle element, non-existent, and random existent, the curve for the middle element has to be the lower one, the random existent should be in the middle, and the non-existent should be in the top, right? But here you can see that the middle element goes over all the other two curves. Okay, and non-existent has sometimes comes below the random existent, which is probably not possible. I mean, so this kind of graph you might also get, and especially for binary search, it is a high probability that you get this kind of unexpected graph. That is because it is taking very less time, and which is basically very hard again for the computer to measure those amount of time. Okay, during the execution. So that's why this for binary search you might get this kind of graph. You might also get better graph, which is expected. Okay, but anyways, uh, okay, so this is what you have to do. Let me show you the insertion shot implementation. So let me close it. And if I come to the insertion shot implementation, I have also implemented the insertion shot. Okay, so again, you have to just, I have just written this amount of code. In your case also, you have to write the code for implementing the algorithm only. No, you have to do not worry about uh, the input and output. Okay, it is taken care of. So again, if you run this, and now we are going to check the insertion shot algorithm. Okay, so for testing that, we have to press 3 to choose the algorithm. I am not getting into the manual testing. Okay, I am directly going into the automatic testing. Okay, so if I go to the automatic testing now, it will take some time, because insertion shot is taking order of n square time, you know by this time. So here the patterns are different. Here we will have patterns on ascending order. Okay, now you know that insertion shot in ascending order takes order of n time, right? Now patterns in descending order, it will take order of n square time. So you can see the variance of time. It is only 3600 nanosecond for 1000 element in ascending order, but in case of descending order of 1000 element, it is taking uh, a whole lot of time. Okay, I have to count the digit if I want to tell you the numbers. But anyways, in case of random also, it is taking much higher time, but less compared to the descending order. Okay, so again, what we have to do, we have to again put this information into the graph. So let me show you the graph for insertion shot, right? So you have to put this information over here and make a graph out of it. Okay, so so size, ascending, descending, and random. So I have done this for my purpose. You do not have to do this n squared curve. Okay, I will show you something extra, but let me first show you. So we'll have the size from 1000 to 15,000, and the pattern is ascending, descending, and random. And in the same way, we'll again do the XY scatter curve with smooth line and markers. Okay, so we'll get this kind of graph. If you look at it, the ascending curve is aligned to the x-axis, but actually it is not over the x-axis. It I mean not on the x-axis. It is just over it. But since the other curves are having higher value, it is looking like it is just overlapped with the x-axis, right? But if you can zoom over here, if you can zoom on only the ascending order, you will find that it is not in the x-axis. Okay, because just because for the descending for the values of descending and random is pattern is very high, it is basically giving looking like that it is overlapped with the x-axis. Okay, so the blue line is our ascending, which is over here, and the orange line, which is basically descending, which is over here. uh, the 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 gray line, which is basically for random, is over here. Okay, now this is n square curve. Okay, the blue I mean the yellow one is n squared curve. It is over here. I am just trying to compare how the n square graphs looks like compared to this one. Okay, compared to the original charts. So let's not go into the n square at this moment. So this is how the graphs look like. Okay, now if you look at it, I mean the graphs basically just looks like the n squared curve, right? And like the yellow one, right, which is for n square. So for descending order, it is almost like n square. For ascending order also, for random order also, it is also having following the n square kind of graph, right? So this is how it looks like for Marshall. Let me show you all the graphs how it looks like. So for Marshall, we also have this kind of graph. The blue one is ascending, uh, orange one is descending, and this one is random. Okay, ash or gray color is random. So since this, I mean, since in Marshall the input pattern doesn't matter, so these three can cross each other at any point of time. Okay, so no worry. Quickshot has some interesting case. You know that for Quickshot, the ascending and descending order gives you the uh, order of n square, right? So then you will find that this blue curve, which is for ascending, and the orange curve, which is for descending, follows some kind of n squared curve. Okay, the blue one, the yellow one is for n squared curve. So you can see that the graph for the ascending and descending order is following for the n squared curve. Okay, and the random order is going to have n log n curve. So that's why, I mean, since the value is very low, it is just looks like it has overlapped with that. And in case of Quickshot, again, all the three cases have n log n time complexity, so they can overlap with each other. Okay, so so this is what we have to do. We have to so for binary search also, uh, so for binary search, the patterns are for middle element, non-existent, and random existent. For all other sorting algorithms, we have patterns for ascending, descending, and random. Okay, uh, now coming to the insertion sort. So this is how we have to do, and let me show you something which you do not have to do, but for your fun, um, for your thirst of knowledge, or for your doing it by your own hand, you can do one more thing. You can also, as I have done you, that we know that insertion sort, the upper bound for insertion sort is nothing but n square, right? So that's why I put n squared column over here. And again in Marshot, I have also put n log n column over here. In Quickshot, n squared over here, and in Quickshot, n log n column over here. Okay, now coming back to the insertion sort. So what we can do now, if I put n squared over here, now what I find is that I find that the n square curve is not over it, not but it is somewhere in between, right? Somewhere between the descending order pattern and random order pattern, right? But we know that n squared is going to upper bound at some point, right? Now if you remember the theory of complexity, what we have that the n square curve is upper bounding. The definition says after a value of n0. If we multiply the n square curve with some constant c, then only it is going to give you the upper bound, right? Then only the YOLO curve is going to up. Now the thing is, can we find the constant value, the c value, which you are going to multiply with the n square curve, and have an upper bound of this graph from this information we have, from this timing information we have? So yes, we can do that. So I am doing it for insertion sort, and this is again not necessary for your course, but for your knowledge, for your excitement, or for your enthusiasm, you can do it. Okay. So how you can do that to find out the factor for this information? Let us so what we have to do, we have to multiply it with some constant factor, right? Multiply the n square curve with some constant factor. So we have to find out the constant factor, right, for which it is going to upper bound all the cases. Now see, what we will do, we will just find out how much factor it is, uh, by how much factor the cases of ascending, descending, or random is basically uh, having I mean, what is the factor with respect to the n square curve. Okay, so let us do that. For though for in case of insertion sort, I do not consider the column for ascending order to find out the value of c for this curve. Okay, I can only do it by finding out the factor for descending order. But in case of Marsh sort and Heap sort, you have to take both all the three columns. Okay, and that's why I'm doing it with all the three columns. Okay, so let us first do it with a factor for ascending order. And what we'll have over there, so we are doing this column, that is ascending value for 1000 divided by n squared for 1000. Okay, so we'll have this column ascending order, which is basically b2, divided by this column, okay, which is basically e2. So it will give me the factor, right? So let us now drag it to find out the factor for all the columns. Again, for insertion sort, this is going to be less than 0, because this ascending order column is nothing but linear, whereas the n squared is having always higher value. Okay, so this is going to be less than 0 always, I mean less than 1 always, not 0. Now for d factor, for descending order factor, again we will do the same thing, but for the column of descending order. So we'll have a equal sign, then we'll select the first column of descending divided by n squared column. Okay, so this will give me the factor for that one. Okay, so I am having factor 1.2. Now if I drag it, so I will get factor for all the 15 cases. Okay, so all of them are 1 point something like that. Okay, now for the random, if I tell it R factor and do it in the same way, so is equals to random divided by n squared. Okay, so this will give me the factor for the random. Okay, so now we have all the factors over n squared for this ascending, descending, and random cases. Now to have an upper bound, what do we have to do? We have to have a factor higher than the highest factor in all these cases. Okay, so we have 1 point something, 1 point something over here. So if we have a factor 2, okay, then probably our n square curve is going to upper bound the all the ascending, descending, and random order. Okay, so what we have to do, I will add another column over here, which will calculate nothing but 2 twice n squared. Okay, so what we will do, that we will just do nothing, we'll do twice into this n squared value. Okay, and we'll drag the value. Okay, so if I just expand it, so we'll drag the value. So this is what we get, twice n squared. Now what we have to do, we have to put it in the chart. Okay, to find out whether it is giving an upper bound or not, right? Now For doing that, to include this in the chart, just right click on the chart and click on the select data. Okay, and over here the chart data range, click in this icon, and then it will give you the option for selection. Okay, so then you select the whole table, okay, including the twice n squared column. Now once you've done that, and if you click OK, now you'll find that the twice n squared column, which is given in indigo color, right, or sky color, now it has come into the graph, and you can see that the twice n squared is giving you an upper bound for the cases, right? So similarly for all the algorithms, you can do this. You can find out what will be the factor for the upper bound. So if you remember the order of n squared notation, there you have two factors, right? One is two integers, one is n0, another is c, right? N0 is after which point we are getting this. So here we are having the initial value of 1000. So after 1000 or from 1000, we are having this twice n square curve as an upper bound of the curve, right, of the curves, right? And there are the value of c. So the value of c is nothing but 2, right? We are multiplying 2 with the n square, right? So from this also, I mean, for this data we have c is equals to 2 and n0 is equals to 1000. Okay. Now similarly for merge sort, quick sort and heap sort, once you do that, I mean, you can do that if you wish. Okay, I have just shown you the way. But anyways, coming back to what we have to do in the lab, you have to for the binary search, for merge sort and quick sort, you have to implement this algorithm using this framework, and you have to get those data. You have to make this chart, okay, and you have to show these things to me.